Okay, so welcome back. This is part two. You should have seen the first video that I made related to concave mirrors. That's where I was using some ray tracing, it's called ray tracing, to figure out what kind of image we're going to get when we have an object in front of a concave mirror. So I did two examples there, this first one, and then the third one here. What was different about the third one was that we moved the object really close to the mirror, and we found that instead of being flipped over, it was upright, it was also magnified. So now we're going to do the same routine, but we're actually going to just use math. So all of this could be done without these complicated diagrams. Well, I shouldn't call them complicated diagrams. They're diagrams. They're actually not that hard to make, but they're a little time consuming. So here's an alternative using just mathematics. Now I'm not going to get into the basis of the mathematics. I will tell you the equations are relatively simple. I put it on the reference page that we're using this here. And the equation that we use, here it is in one form. It's known as the mirror equation or the lens equation, and it relates how big an image will be compared to the object, and it also relates to the shape of the mirror. So these are spherical mirrors. They can be concave or convex. These happen to be concave, and the shape is going to determine what we call the focal point. So the focal point can move closer or farther to the mirror, and however far it is from the mirror, that's called the focal length. We give it the symbol F. So that's what this F here is in this equation. This same equation can be written in this form. I actually use it more often in this form because the way I tend to ask my questions is how big or how far is the image from the mirror? And that's called DI. So DI is the distance that the image is from the mirror. DO is how far the object is from the mirror. And F is how far the focal point is from the mirror. These are all just numbers that you get from the problem. They're all a little unique. We're going to get them right from the diagrams, and then I'll show you how we can just plug those into the equation and get it. The basis for the equation that we're using here, it's all in geometry, but it's complicated enough geometry, I'm not going to try to prove it to you. If you want to dig into where that comes from, knock yourself out. There's plenty of information on the origins of the mirror equation. You might also hear it called the lens equation because we're going to use the same equation when we study lenses. It's just all about how light will bend when it hits something. Does it hit a mirror and reflect, or does it hit some kind of new medium and bend or refract? Okay, for now we're going to deal with just the reflection part. We're also going to find out how tall or how short our image will end up compared to the original object. That's what we call the magnification, the height of the image compared to the height of the object. So if it's twice as big, the height of the image would be 2 compared to 1 for the object. That's a magnification of 2. In the first example I did, you might remember, the image came out about half as big. So the magnification there would be a half, but it's also a negative because anytime the image ends up flipped over, we call it a negative. That's part of what we call the sign conventions. So the sign conventions are that the image distance will be negative if it's a virtual image, but the image height will be negative if it's an inverted image. Okay, so one will be negative and one will be positive for every example that we have here. All right, so let's dig into this. So the question again might be, what is the location of the image? So that's what we'll call the image distance, DI. And I'm copying the second form of the equation because it's more convenient, okay? Because it's already solved for what we want, right? I promise you this is identical to that. We just, instead of writing it as fractions, we write it as powers to the -1, just a little easier. And I have solved for DI. So I did a little algebra manipulation to get DI by itself. It just involves some subtraction, okay? And, oh, I just noticed this is missing. Your copy should be okay, because I'll give you a better copy. But this is missing a power of -1. Okay. So I'm going to plug the numbers in that I see from the figure. So on this diagram here, our focal length was 1, 2, 3, 4, 5. From the mirror to the focal point along this principal axis. So that's a 5. I'm not putting units in just to avoid the clutter on this page. And then the object distance. So here's 5 more, and then 1, 2, 3, 4, 5. So 15 is the distance that the object is from the mirror. Okay, so we're going to take the inverse of 5, subtract the inverse of 15, and then we're going to invert that. That's what this -1 here is, and it will give us the answer. I'm just going to pause this, run this through my calculator, and we'll see what we get. So here's what I put in my calculator: 5 inverse minus 15 inverse, and then inverted that. And I'm in scientific notation. I'm just going to change this to what we call float mode. There we go. 7.5. Now, that is a positive number. It's actually a really good match for the diagram. That doesn't always happen quite that closely. It means I did a good job with drawing my rays because I know the math is perfect. But the fact that that came out positive tells us something important. It also tells us that this is a real image. Okay? Real is always associated with a positive distance. That means it's on the front side or the real side of the mirror. Okay? Now, once we have DI, we can calculate the height of the image. That's kind of like the size, if you will. So, looking back here, you got to be careful because there will be a negative sign as part of this equation. I'm using this form here. Negative sign has to come with it. HO, that's the height of the object, times this ratio here. How far is the image compared to the object? So, I always write my symbols first, and then we'll plug in the numbers. So, the height of this object, again, we have to get that from the figure. 1, 2, 3, 4, 5, 6, 7. I try to make them a whole number. I'm keeping the centimeters off. Okay, everything in this will have centimeters. The image distance, now that we found it, 7.5. The initial object distance, remember, we found earlier to be 15. And so that image height, I'm not even going to do this on my calculator because I know this ratio of 7.5 to 15 is a half. So a half of 7, throw the negative on there, negative 3.5. Now I'll go ahead and put the centimeters on since I'm done. And again, a very good match for what we got when we did this with our ray diagram. And the convention, again, the convention is on this page. If the height ends up negative, that tells you that it's inverted. Okay. So if you didn't know because you hadn't done a ray diagram, then this number is how you would tell. All right. So that's really all there is to it. I'm not even going to do this one because the math, there's nothing unique about any of these. The math, it looks pretty much the same. The only difference is when you get a positive or negative. I will tell you on that third example, you're going to end up with a negative image distance. A negative distance sounds kind of weird, but the convention is, or they've just figured out to make it work out so that we could tell, if you get a negative image distance, you're dealing with a virtual image. Okay, that's what will happen in that third one. So kind of be ready for that. All right, I'm going to stop my demonstration there. Hopefully you can work through the rest of these, and if not, of course, you can find some help. Thanks for watching.